Okay. Welcome everybody to lecture 9. We continue our discussion on PCPs and their application to hardness of approximation. Today's lecture will be focused on unique games and the subsequent consequences. There's a larger audience today, so I'll sort of, the first 10 to 15 minutes, I'll put the context back where we are and then get on to issues. So, what was this? The recap of where we are in the course. So, this course primarily deals with trying to prove hardness of approximation of several problems. So even before that, we've seen that the starting point was to actually these approximation problems were actually problems which were originally the original optimization problems that we proved to be NP complete. This is back to work in the 70s and 80s, in which we started with more or less Cook and Levin's point. This was the starting point of all this, and this led to a whole bunch of NP complete the NP completeness of the several optimization problems, combinatorial optimization problems. And this was an extremely successful area. This one we were able to show several problems that we hadn't yet come up with algorithms. Actually, the reason we were not able to come up with because they were as hard as SAT. They were as hard and no harder than SAT. They were actually because we were able to show this sort of a whole web of reductions. This is usually done in any introductory course on the complexity basis. Subsequent to that, people ask, okay, these problems are not okay, they are hard to solve exactly. What can we come up with approximation versions of these problems? For example, there are several problems you can take for example, max 3SAT. 3SAT, the problem is never stated in an approximation version. It's given a 3SAT instance that is given a bunch of clauses of 3 variables each. The usual problem is, can you find an assignment that satisfies all the clauses? Now let's try to make this into more like an optimization problem. Let's frame it into one in which you're given a certain instance and you ask to find out an assignment that satisfies the maximum number of clauses. If the maximum is everything, then it's satisfiable. Otherwise, whatever. You can ask this problem. And this is also certainly this is NP hard because this is harder than the other problem. And you could ask, okay, if I can't get the maximum, can I get 99% of the maximum? Can I get 90% of the maximum? You could ask these questions. And it's easy to see if you just pick a random assignment, completely ignore the instance, pick a random assignment, you'll be able to satisfy 7/8 of the clauses. Because a random assignment satisfies a single clause with probability 7/8. Therefore, an expectation it satisfies 7/8 of them, and this can easily actually be randomized. You can come up with a deterministic algorithm that satisfies 7/8. So we know that it is hard at 1, easy at 7/8. Where does the transition happen? Similar, this is one such problem. Because somewhere along the way, it should transition from easy to hard. Is this a sharp transition? Is this a gradual transition from? So this is one such problem. Another problem we can take is vertex cover. Vertex cover, we know finding the minimum vertex cover is a hard problem. So, once again, it's one of the classic NP complete problems there in Karp's original list. And for this, we could come up with an algorithm. It's easy if you find out the maximal matching in a graph, just output the edges of the maximal matching, you'll notice that that's a vertex cover. And that you can show that this is actually within a factor of 2 of the smallest vertex cover. So you can get a vertex cover which is no more than twice the size of the minimum vertex cover. So this is something different. So the smallest vertex cover is hard to obtain. You can get a 2-factor approximation. Question once again is where does the administrator? So these were problems for which we had easier approximation algorithms. Then there's other more richer problems like max cut, where the random assignment satisfies half. Once again, you can satisfy half the number. You're given a graph. What's the problem here? You're given a graph. You want to find a cut in the graph that maximizes the number of edges. You're given an unweighted graph, and you want to find a cut that maximizes the number of edges being cut. You want a partition of the vertices in 2 parts. And for this, it's easy to, if you pick up a random partition, it's easy to show it cuts half. For a long while, we felt we did not know how to move around this. In the mid 90s, 94 exactly, Gomez and Williamson came up with a semi-definite programming based algorithm which gave a 0.87856, which is called the Gomez and Williamson constant today, an approximation algorithm for this problem. So once again, so that's easy, one is hard, where is the transition? And this was constantly asked in all of these, and then somewhere in the early 90s, people realized the PCP theorem. So I won't state what the PCP theorem is. The PCP theorem was proven, which seemed to be useful to understand where this transition was able to show certain approximation versions are also hard. That's not just for vertex cover, not just one was hard, but something smaller than one was also something larger than one. One was hard, two was easy for vertex cover. Question is, where does this one? The PCP theorem showed that beyond one also there were certain things which were continued to be hard. And then subsequent developments in the PCP theorem, work with related to PCP theorem, led to what is called the parallel repetition theorem. And based on both of this, there was something called the label cover problem, which was then studied. So I won't state the PCP theorem or parallel repetition. What I will instead state is the label cover problem, which is going to be which the unique case is going to be a special case of the label cover problem. So what's the label cover problem? The problem is of the following type. The instance is a graph, in fact, a bipartite graph, U, V, and edges. The bipartite graph, so you're given U and V, and some edges across. It's basically a sort of a coloring problem. But usual coloring problem is the fact that on an edge, you specify a set of colors and you want to color an edge so that an edge is non-monochromatic. But here what we do, so we specify colors. The colors will be different for the left side and the right side. So this is what we call, these are sets of labels. We're going to have two sets of labels. And in the coloring problem, usually the constraint on an edge is these two colors are distinct. Here we have a more sophisticated constraint. The constraint will be, so we'll be given a set of size. And psi is going to be itself, each of them, each side itself is going to be, it's going to take a pair of colors as input and say whether this is a valid coloring or not. The psi is just a set of constraints on the entire thing. These constraints could depend on each edge, and that's so the instance is specified. Instance is just this. Okay, you're given a bipartite graph, a pair of labels, a set of labels for the left side, set of labels for the right side, and a bunch of constraints for every single edge. And what we'll say, so this is P. So that's the label cover instance. And what is the value of this label cover instance? It is an assignment to the left side and the right side from the respective labels that satisfies the most number of constraints. So it's the max. It's the max over all labelings of the left side and all labelings of the right side of the probability. If I take sigma, and I pick a random UV edge from this one, that psi UV of A comma U, B comma V equals 1. This is the now it's a fraction of the edges satisfied by this particular pair of assignments A and B, and you want to maximize this over all. And the gap label, the gap CS label cover problem, let's just call it LC for short, is a problem in which the instances are exactly the problem instances are label cover instances. But the S instances are those for which the val of P is greater than or equal to C. So 0 less than S, less than or equal to S, less than C, less than or equal to 1. So the S instances are those instances for which you have a coloring that satisfies more than C fraction of the edges. And the no instances are those instances with P. Such that this happens, which is P, that the val P is less than or equal to S. And you want to tell the part these two. There's already a gap. The gap is between C and S. And this, all the work starting from the PCP theorem plus parallel repetition if you put all of that together, you get the following theorem, which is basically a hardness of gap CS verified. It goes something along the lines, which basically states for all delta in 0, 1, you give me a delta in 0, 1, there exist labels sigma u and sigma v, where size of sigma u and size of sigma v is poly 1 over delta. The labels are just poly 1 over delta. And such that here is a order n to the log 1 over delta time reduction from stat to gap 1 delta. That is, you could reduce SAT to label cover in which you can't tell differences between difference between instances of the which are perfectly satisfiable and at most delta size.
Order n log or n or n to the power order.
Yeah, that's the order the O. So for all constant delta, this is a polynomial time reduction, and this is what we spent a fair amount of previous 8 lectures in the course to prove this theorem. So let's take this on faith. So let's take this. Okay. So any questions on this? Many games is going to be a further modification of this.
So if one change something smaller, that is then is it an easy consequence or that's a separate?
Which one?
So if you change one to something less than one.
The problem is 1% is change something less than 1.
That's not.
No, that's easier than this. So even this is hard.
Yeah.
Even
But it's formally easy, like this.
It's a formally this. If I
Because if you can solve this.
if I can solve that, I can solve this.
Yeah.
I can solve that, I can solve this. So yeah. Fair enough. So this was problem. So it's a very specific type of. You can think of this as a SAT-like problem. The reason this is sort of the reason I'm sort of putting this up is in the 70s, 80s we had this. The starting point of between hardness of several optimization problems was SAT. The SAT was the mother of all hardness reductions. And For trying to prove approximate problems, what happened to become the starting point was actually gap algebra. So the sort of research in the actually all the way till today. So the entire research starting from research in inapproximability from late 90s onwards. It sort of replaces that picture which we had. So it was gap, one delta label cover. And from that, we could prove a whole bunch of these optimization problems. For instance, what you could prove was gap 1 versus 7 by 8 plus delta max 3 sat. So max 3 sat, we said previously, 1 was hard, 7 by 8 was easy. And this basically states that anything better than 7 by 8 is also hard. 7 by 8 was the hard. And we could get that sharp thing because we knew this. So this was due to Haskell. There were a whole bunch of several such problems out here. We had in class, we had done gap 1 minus epsilon half plus delta max 3 then. It's like SAT in which you're given a bunch of, instead of now clauses, you're given a bunch of linear equations over GF2 for the finite field, and each equation has at most 3 variables. So 2 stands for GF2, 3 stands for each equation and 3 variables, and you want to solve the system. Once again, if the system is perfectly solvable, it's trivial to do it because you can just do Gaussian elimination. It's easy to satisfy half, just pick a random assignment, it will satisfy each equation with probability half. So 1 is easy, checking 1 is easy, half is easy. Question is, so if it's between these two extremes, these are easy. Tell it's 1 or tell it's half. Now I'm going to change 1 to slightly 1 minus epsilon and half to half plus delta. And it says at that point, it's now, you can't tell apart. If I give you an instance from 1 minus epsilon or half plus delta, you can't tell them apart. What does this reduction mean? If you could tell them apart, you could tell apart gap label curve between these two instances. And then coupled with this previous theorem, that will say I could tell apart SAT between its S and no instances. Therefore, you have this whole putting all these reductions together. You say that if I can tell these two apart, I can tell SAT. This was the state of affairs. So we had this for several optimization problems. The several optimization problems, we in fact got the right inapproximability gap. We got the exact threshold, and we were able to. A couple of them escaped this. A few problems.
Well, is there a reason to expect that there should be a sharp threshold?
No, there is no reason to. So, actually, it was a very sharp. It was a very big surprise. Then people sort of wanted to relate it to sort of the threshold phenomenon and physics and all, but that didn't.
But there's some group with algebraic. There's some algebraic post factor explanation. Something. Everything there's certain algebraic structure will have this kind of.
Yeah, but it doesn't say that other things will not have.
Yeah.
So it only sort of generalizes these proofs and says that more and more when the problem has been structured, then it will have this sort of a sharp transition and stuff. But yeah, I don't know.
So there's no shape for type dichotomy yet. There's no dichotomy.
Oh no, there are shape type dichotomies for shape type dichotomies. So what Piyush is asking is the following question. So these are all max constraints, these are max CSPs. Now, given a max CSP, you can ask is it perfectly satisfiable or not perfectly satisfiable? This is the problem. And Schaefer had this result that said that you tell me what is the type of CSP, based on it, I can tell you whether the corresponding thing is NP complete or P. It can only have one of these two. It cannot have polymorphisms. The polyethylene polymorphisms. So there is a similar such thing, at least for all the max CSPs, you can do this. Max CSPs, you can more or less do this, except for a catch. The max CSP we'll come to that. If the max CSPs have arity 2, then we don't, then for some reason, this reduction sort of, so for example, max T sat, max T didn't do all of them, the each constraint had arity 3. And we could handle them. RP two things escaped this reduction, and we did not survive. It's not felt why we could escape, why we could not prove it. Analytically, the reason was the proof was somewhere around the proof we used Fourier analysis, it was a Cauchy-Schwarz or something going along the proof. We had only quadratic terms, we needed results on something more, we had to get more terms. There was not enough freedom to do the proof structure, but that's just stating that why this particular proof did not work. And there were several problems along this one. A few problems escaped. A few problems. In particular, which ones? Let's say problems. Example, prominent among them being max cut. That's once again, remember, max cut is an arity 2 problem. You're given every constraint is an edge, and you ask, it's basically an edge, and you have to color it with 2 different colors so that that's the constraint you have. Max cut. Vertex cover, it's not a max CSP, but it is a max CSP problem of this type is max 2 set. So 2 set is easy, but you can ask the maximization version. Find, given a 2 set instance, find an assignment that satisfies the most number. This could, we know that this is at least as hard as 2 set. 2 set is easy, that doesn't mean that this is easy. This happens to be actually NP complete. NP complete. So you want, if it's perfectly one, you can check it out, but anything other than that is hard. And you wanted to get a sharp threshold for this. This also seemed to fail that.
So every CSP code which we know a threshold unconditional reduction to set, those are arity
Greater than equal to 3.
and arity 2 constants are all based on the ranges.
All I don't know,
But
most of them. Actually, so GFO is the variables are taking values in GF2, I can say now. If you're going to take variables, you can talk about max field in over some larger field and stuff, or you can come up with more complicated constraint satisfaction over a larger alphabet, that I don't know. They all seem to have this feature. So now question was asked. So we had SAT was our starting point for NP hardness results. Gap 1 delta label curve was the starting point for several of these. It proved as a good starting point. Question was asked is, can we, so is this starting point weak enough to prove for max cut and vertex cover, or is it the failure of what is it that we need? Is there reduction? The proof, this reduction, these proofs were primarily these are fast like proofs. We already, this entire area was sort of started off with 2 seminal results of FASTA, one for the clique and one for these 3-lin. We did the 3-lin in class, clique we didn't do, but this was started with FASTA using Fourier analysis of this. And question was whether these reductions were weak or the starting point was weak. It could be the combination of, you don't know which one, there could be a proof which does this. And so it's not that these problems, the max cut, it's not that max cut. It's not that max cut or vertex cover did not have enough approximate results. For example, vertex cover. So for max cut, we could show something better than half. Better than 1. So 1 was easy, 1 was hard, 0.87856 was easy. Some number, I think 0.91 was 91 or 93 was shown to be hard using the same that was shown using a sort of an approximation preserving reduction from 3 sat to max cut for this one. And for vertex cover, for a while it was open, we want to get the best hood of the best constant. And here came the work of Irit Dinur and Moli Safra, which is part of Irit's PhD work, in which they showed that vertex cover, once again, what is the status for vertex cover? 1 is hard, 2 is easy. They showed that you could get some 1.365 was also hard. 1.365 was significantly, it's better than 1, but it's not yet 2. They showed this. And in fact, in that, in the proof, it's an extremely well written paper and it's a remarkable result. They brought in a new set of techniques which are different from what FASTA had. brought in. So we will see this in the second part of today's lecture. This was brought in by Girit and Mooney. And in fact, they sort of said, we can hope to get a better hardness if this gap, their starting point was also gap 1 delta label cover. They sort of said, if this gap 1 delta label cover had some better structure to it, our hardness reduction could be improved. And what structure do they ask for this? The structure they sort of ask is, if you look at the gap thing, let's look at these constraints. The constraint says, what are the pairs of labels that satisfy a given edge? For every edge, it tells you this. Now, there are specific types of these constraints called projection constraints. Which are of the form phi E is sigma u to sigma v. There's a difference between relation and a function. Relation is just arbitrary pairs of labels. This way, if you give me this label to the left side, this is the label to the right side. That is, for every label on the left side, there is a unique label on the right side that will satisfy them. That's the difference between a function and a relation. So these are called projection constraints. And in fact, the gap label cover that was proved here was actually this theorem actually yielded even gap label cover with projection constraints was NP hard. And in fact, this property was used in all the reductions, which this entire web of reduction convention here. Now you could ask, but this with projection constraints actually later on there is a without loss of generality statement. You can convert a label cover to another label cover with projection constraint. You could add this. I'm not going to how it is done. Though the original reduction managed to get it with projection constraint. What Devur and Safra felt, what the projection constraint says? Projection, so if you look at, let's look at a particular edge. Finish the sentence, escaped. Optimum. Particular Devur Safra. It could have 1.3 something hardness for vertex cover. And so let's look at the nature of the constraints. So I'm taking one edge, UV, and there's this constraint psi u sitting from u cross v to 0, 1. So this constraint, I'm going to view this itself as a graph between sigma u and sigma v. So this is all with just, I'm focusing on a particular edge UV. And what's the constraint setting? It's these edges are all valid edges. This is not the bipartite graph. This is the graph between two sets of labels, and let's say these, if you give me these labels, it's valid labels. This is an arbitrary constraint. This is an arbitrary constraint. A projection constraint will be of the following type. Projection constraint.
The relation is the function.
Yeah, basically, this side will have degree 1. This side need not have degree 1. So that's a projection constraint. Something called a 2 to 2 constraint is a constraint of this form. Every guy here has possibly two guys that satisfy this. Okay, this is a very special 2 to 2 constraint. It looks like this. Every guy here has two guys on the other that satisfy, every guy there has two guys with this. What sort of the rules are provided was, and you could think of more like M to M or D to D. They said if the constraint graph had this property that was D to D for a small constant D, then their reduction could be actually improved and you could get numbers better than 1.3. And they left it at that. This led Code to sort of look at this problem a little more closely. And Code then made the bold conjecture that possibly this problem is hard, even when you have the constraints are unique, that this is just a permutation,
Just the one, two.
one to one.
So they said it can improve if you have a smaller D, that was it.
That was, this was written as a bunch of remarks. The paper itself was a long paper. They said, what can be done to improve 1.3? They sort of made the sort of statement that our things will improve if we can get, if one gap, one delta label cover, if this hardness, if this theorem, we could prove it even with, for instances, specific where D was small.
So,
And he said difference.
in this case, both the alphabets have the same cardinality.
Yes, both the alphabets have the same kernel.
But in the reduction from PCP to get level cover alphabets.
Then you can, there is a way to make that of the same size, the way to make that of the same size. So, the Linus software sort of, this was just written as a remark in their paper. Code actually went ahead and made this bold conjecture that possibly they said, okay, this is a, you can do this. Why don't we actually assume this? So Code actually conjectured in 2002. That is, so what can he conjecture? Let's see, what could he have conjectured at that point? You want to conjecture the one to one. You wanted to say, okay, the question you wanted to ask that. So once again, we're going into this picture. So we were not for these problems like max cut, vertex cover, max to sat. We were not able to prove optimal in across results like these guys had. So either it is the fact that these techniques are inadequate, or this starting point is big enough. Of course, this you can't pinpoint this. It's possible that you could, with this starting point, you could still do it. What? The Linus software results seem to suggest that if this had stronger properties, then their proof could give an even better hardness for vertex cover than what they did. So Subhash then said, what if we ask the best we can ask up here? Then are these techniques over here good enough to get the results we want? So he said, okay, let's then make this assumption. Let's assume gap one delta label cover is hard, even with one-to-one constraints. I don't know how to do this, but given this, can we do something? So he went ahead and made this, what is today called the unique games conjecture. So his thing was basically to answer, are these techniques strong enough? If you make a wild enough assumption here, of course, you're going to go to wild assumptions, you can make all the way, you can make a false assumption from which you can do anything you want. Question was, how weak an assumption you have to make so that using these techniques, you could go and prove the results that we haven't yet been able to. So he asked, what's this one? And he noticed that given the Linus software result, it's possibly better to assume, let's assume one-to-one. Now, one-to-one is, you have to be careful when doing it. So let's look at it. Suppose one-to-one, I want to claim perfect completeness is an easy problem. Because if we had such a result, and if I said there was an assignment that perfectly satisfies all of them, one-to-one should be easy because I start off with some vertex. It has, it has a finite set of possible labels with. For each such label, start the label. That will tell you immediately what are its neighbors. And then they will tell their neighbors. The entire connected component you will know. And at the end of it, you can check if this is a valid this one. If that's not, start off with a different coloring labeling for the first vertex and go ahead and just spread this out. You can check it. So for one-to-one, checking if it's perfectly satisfiable is always an easy problem. It's just one of these values. You can just propagate it. Each connected component, you just do this separately. Graph and you can sort of figure this out. So you can't assume that gap one delta label cover with unique constraints is hard because one is an easy. So because of that, given that Code actually, his conjecture was for all delta in 01, there exists a label sigma, and size of sigma was some function of delta. I don't care. Right now, it's just the constants, such that gap 1 minus delta, delta label cover, even with unique constraints.
1 to 1.
Unique, this is,
So delta should be within 0 half, right?
huh? No.
I will minus
So yeah, so this is at most, yeah, I think, okay, the delta should be smaller than half. Yes?
If it's allowed to grow arbitrarily.
If right now I'm allowed to, so if you can show it for some, f that just depends on delta. So he makes, and he of course makes his original page as his entry harm. That's the conjecture. And so given this, so now, so this is, we will, so I'll call, so let's call this label, label cover with unique constraints. Let's call it unique label cover, so this is actually US. So now, court question was, why did court ask this question? Court question was, suppose I had assumed gap 1 minus delta delta ULC. What more can I get here? So do our techniques now, given this assumption that I have made, can I go ahead with other Fourier analysis techniques strong enough to pass these results? And in this very same paper, what he did do, the case he made for this was he proved a root 2 hardness for vertex. Okay. And so he said, if you make this harder assumption, if you make this assumption, a weak assumption which is we don't know how to do. Previously, gap 1 delta level curve was what was true. If you can assume that the unique version of it also is hard, then he could modify the existing reduction to get a square root 2 hardness for the vertex. Okay, so the stronger assumption does question. So in fact, he didn't leave it as a conjecture or something, he just called it a hypothesis. If this hypothesis were true, we could do this. So it's worthwhile trying to work on this hypothesis and see if we can. Well, now it's called the conjecture, and there are, in fact, even till very recently, till about 4 years ago, there are still people strongly divided whether this is the conjecture people believe in or not. Till the 2 to 2 thing was proven. There were there's one stating that SDPs are possibly powerful enough to disprove this.
What happened 4 years ago?
We'll see that later on in the course. There was basically 4 years ago, the same thing was 2 to 2, not even 4 years, it's more recent than that, or possibly it's pre-pandemic. Okay. The 2 to 2 theorem, the same thing with 2 to 2 was shown to be hard. We could get it all the way down to 2 to 2, not to 1 to 1. Okay. Okay, so the courts sort of conjectured this. Once again, this the note that was in her graduate study, court was this was in a, I think it was the final year of this graduate study, he made this bold hypothesis and said from this, it will result in a plethora of the. And immediately after this, they realized that UG was extremely powerful. From UG, several other problems whose hardness which we did not know how to handle, we could now get optimal response. So right after courts 2002 paper. Came a result due to Potregev. Where they looked at Dinur Safra's 1.3 hardness for vertex cover. And they said, what can we do? They already, Dinur Safra had this statement saying that if we could do, we had a SADA assumption, we can do it. Court had already done it in the square root 2. They showed that actually you can get 2 minus epsilon hardness for vertex cover. The vertex, the if UG were in fact true, that two approximation that we saw at the very beginning of lecture is 5 for vertex cover. You can't do anything better than that. That was quote again.
Dinu Sabra's result was under what assumption?
NP not equal to. So till quote came into the picture, the assumption was always NP not equal to P. That's the.
No, so that constraints like there they didn't agree.
They didn't assume. They said if the thing is the if they had only assumed they only assumed hardness from SAT because SAT was hard. This theorem says this is hard, and they started to talk from this theorem. But they said if this theorem you could do it stronger with in which the constraints were D to D, then our proof will give you better results. But they were not able to do this, so they left it at that. Quote goes ahead and then makes a thing. Let's be brave, and he said let's go assume that this constraint graph actually looks like a permutation. It's just a one, it's a matching. And then he said, and there's place for this because with that I could prove root 2. And I know immediately after quote, Oded and Subhash Quote were able to show that quote's assumption, quote's hypothesis actually led to not just by root 2, it actually led to a 2 hardness for vertex cover. Then there was this quote in the Moser from November. Oliskevich. They actually showed max cut, which had this. So even this was not, didn't sort of shake the community that much because it was the same sort of tools that were used. They said, you can make, if you make a wide enough hypothesis, you can prove everything. So possibly that's true. The interesting thing about this result was it said that you could actually get Gomez-Williamson's constant. It's a geometric constant, unlike this 2 and square root 2 were things which flew from Fourier analysis very clearly. They actually showed that Gomez-Williamson algorithm is optimal for max cut. And since then, there have been a whole variety, almost all, I won't say all, most of them, all the 2 problems which we failed to get it, they have now been able to prove optimal results, assuming UG.
So here does the 0.878 come from the same minimizing cost theta by 1 minus theta?
We will see this. So what I will do in the rest of the lecture is you'll see both these parts.
So 0.878 comes from the same minimization.
Yeah. But you see where it comes from. It comes from one. So by the way, when KKMO proved this result,
It comes with the integrality, I think.
huh?
It's in the hardness, does it come from the integrality, I think, like that whatever that.
It's sort of they're all eventually you'll see they're all the same. As you will say the proof and then we will.
That just little graph on the like the cap.
It's going to come from that. You will see that. You'll see that shortly later. So when we proved this result, actually at the time of KKMO, not only UG was the conjecture, so this KKMO is a conditional result. But it was not just conditional UG. There was another theorem which was also not yet proven. Then they needed something for the majority stabilist. They conjectured both these results and then they were able to prove this. But immediately after KKMO result, Moser or sorry, this is not. This is not.
Yeah, that one
This is O'Donnell.
Majority is stabilized first.
Yeah, so Moser, O'Donnell, and Oliskevich, then proved the majority stateless conjecture, they actually proved it as a theorem. And therefore now KKM result depends only on one unproven conjecture, which is Port's conjecture. And that's the status today. And then since then there's been several works in optimal mean approximability results. So this is from the hardness. Obviously, once you have such a thing, the people from the other side, that is algorithms, now want to say, okay, UG is now giving a problem of interest. What's the best algorithms we can come up for UG? So if you break UG, well, so the status was these all problems you were able to show from UG there was a reduction. It was never shown that the reduction the other way. Question is how wide the assumption is UG? How if you show the so NP completeness was a nice thing because you are showing that they both are hard or easy together. So even if one of them you prove to be an easy algorithm, it pulls it. In one of them it proved to be hard, everything hard. No. These results are if you are taking with a bit of this one, it might be that vertex cover is 2 is the right answer for it. Gaussian solution is the right answer for max cut. But yet UG might be an easy problem. Just that because all these reductions are going in one direction. So getting better if you prove these results, that doesn't mean UG is going to. So UG was never shown to be, we did not have a completeness result. So people are also working for reductions going in the other direction. I won't have time to even talk about this. They were showing that small set expansion with this particular type of one that actually does imply UG. So it goes along with UG. So small set expansion and UG is put together. This is the result of Raghavendra, Steurer, Tulsiani, and others. And from the approximation version, from the algorithmic viewpoint, there were lots of works. Probably the most significant of them is the work of Aurora, Barak, and Steurer. That's probably the one. What they showed was they showed that we don't have the polynomial time algorithm that would have beaten the broken level. They showed that you can have something like they gave them 2 to the n to the poly box. Going on, so that's some other person might have started there. I don't know what. Yeah. So what they gave is time algorithm. It was not a polynomial time algorithm, but it was. Am I being sorry? I should sorry. This is not poly 1 over delta. This is poly delta. It's a sub-exponential time algorithm. It's not a 2 to the n. It's this one 2 to the n to the epsilon.
It will also depend on the algorithm.
Delta will always be a function of the alphabet. So we are going to now from now onwards, the delta will govern both the soundness error and the alphabets.
Alphabet is polygon.
Polygon over delta. That's the thing is polygon over delta. They gave such a thing. So, and this seemed to suggest to some people, in the eyes of some people, that possibly UG is not NP hard. Because NP hard problems, you expect them to have 2 to the n running time. The problem is NP hard. This is not fully true. That is, this is true only if the proof of NP hardness is the linear time reduction. If the proof of NP hardness takes n to the power 1 over epsilon, then this is what you would be proving. Then NP hardness will not do this. So this was sort of taken as the reason, sort of one of the reasons why they felt UG was easy was because such an algorithm existed. NP hard problems typically don't have sub-exponential. They don't have 2 to the n to the epsilon type algorithms. It had this, but that is question of what do you mean by so when both assumes it's NP hard, does he mean it's he only a certain possibly he only means it's NP hard under polynomial time reduction. He is not assuming NP hard under linear time reductions. So if something is NP hard under 2 to the n square under n square time reductions, then the best algorithm you can only show is 2 to the square root n. You can't say that it doesn't have 2 to the n time algorithms because of the blow up in the reduction.
It rules out certain kinds of very efficient reduction.
It rules out certain kinds of very efficient reduction.
And ACT,
Huh?
it is assuming ACT.
Assuming
Exponential.
assuming ETH, yes. And to sort of the 2 to 2 result, which was proven few years ago, actually does have running times which are n to the 1 over delta. Running time is closer n to the 1 over delta. So sort of fits into the bigger picture. We don't know where the truth is, but that's where we are. So, questions on it. So this is sort of the introduction to UG, why court introduced it, and this led to a remarkable number of the court won the Never Prize for this. It was possibly one of the few cases prize was given for an unproven conjecture because of the amount of research it has spurred. It's quite a remarkable thing. His court has been working on this since 2002. He's possibly the biggest player in this area, and he's done a remarkable work. And it was this work, it's actually the laying of the conjecture that led to the Never Prize 6-7 years ago. He got the Never Prize before the 2-to-2 theorem was proven. So even before we had some sort of, there was far more skepticism on the UG, on UG's the truth of UG when the Never was given, but it had spurred enough amount of result to justify the price, far more than. So any questions so far? If not, what we will do in the remaining part of the lecture, we will spend about 45 minutes each on max cut and vertex cover and show how UG implies how we improve both the Both-Regehr and the KKM models. Questions? So we'll start off with the UG hardness of max cut. We first do KKMO. So what I'm going to do is I'm going to assume gap 1 delta unique label cover is NP hard, and from that reduce it to max cut. So it's going to be a reduction. It will be just a regular type of reduction that we make. So a reduction from gap 1 minus delta ULC to max cut. So in other words, we already have the gap delta label cover is already a problem like this with U and V. Every edge, when you zoom into an edge, it has a. If you zoom into a particular edge, U and V, the constraint there looks like a permutation. So that's a particular edge. Every edge has a different constraint. Let's, for this one, just assume the two labels on the left and right hand side are the same. We're making an assumption. We may as well assume that the labels are the same. We'll assume this is what it is. From this, I have to now give a reduction to max cut. Then we will say this is not U and V, so this is sigma and sigma. So how will this thing eventually work? So if we sort of familiar a little bit of previous lecture, but otherwise, basically what we're going to do is for each vertex here, it's going to be, unlike the proof of the PCP theorem, this is going to be a very local reduction. The standard NP completeness reduction just looks at the instance and makes gadget reductions. It takes each part to replace it with another gadget, and that's how it goes. So this is what we're going to do. We're going to do is for each vertex here, we will blow this up into a cloud of vertices. this will be changed, but this is sort of the general idea. This was the idea used for max tree learn, and also we're going to blow up each of these into a cloud of vertices. And then we'll possibly put some edges between these clouds. And also, if this cloud and this cloud are connected by an edge, we might put some edges that way also. So this will be the structure, and this will be the graph that we obtain finally. It's going to be this particular graph. The graph on the violet vertices and those edges will be the max cut instance, and we want to show that if this max cut had better than 0.87856 approximation algorithm, then this particular label cover instance, which was the unique label cover instance, I could solve it with, I could satisfy more than delta fraction of the constraints. Therefore, it's not a no instance, so it has to be an essence. That's how the and so this is, I'm going to use some of the past lectures. So what is the cloud that we will blow up here? The cloud that is typically going to blow up here is basically we are going to put the hypercube corresponding to sigma. Basically, for every subset of sigma, we will have a vertex. Hypercube is going to be, see, so this guy over here is just zero one to the L, which is basically 0, 1 to the L. What is 0, 1 to the L? It is set of strings of size of length Boolean string, but each string you would have a possible subset of the set L. So it's all possible 2 power L subsets of the set L. Sorry, L is one. It was sigma. So sigma is what? So you that each cloud will actually be 0, 1 to the sigma. It's basically going to be, and we'll think of them alternatively as strings. We'll think of them as sets of potential labels. Now you have to put it. So let's forget about the cross edges. Let's just look at the internal edges. So I need to come up with a test that I need to put the edges between these two. I need to find out when to put an edge between two such objects. So, how does any cut in this look like? A cut, a global cut is just a, let's just focus on that particular cloud, 0, 1 to the L. How does a cut look like? It's just going to assign certain things to 0, certain things to 1. So, a cut, when localized to one of the clouds, looks like f going from 0, 1 sigma to 0, 1. It's some on this cut. And we want to show that only certain cuts have some properties. In the proof, we will eventually need this. We want to identify, we want to come up with a test that just tests this thing only on 2 points in this space and is able to find out some properties of this cut. This is similar to what we did for max tree learning. We had a function as 0, 1 L. We queried it at 3 locations and checked the 3-lim constraint over it. And what ideally we want to do, inspired by what we've done in the past, what we want to is we want to design, the goal is going to be to design a test that distinguishes what are called dictators from other functions. I'm going to put distinguishes in bold. So what's a dictator? A dictator, so let's remind you what a dictator is. A function f from 0, 1 to the k to 0, 1 is a dictator. It's exactly what dictator is. It says if the function depends on k coordinates, the dictator is actually f of x if there exists a I in k such that f of x equals x. Basically, it just takes the ith bit and outputs. So the ith guy is the dictator. It's not actually a function of the whole thing. So a lot of the terminology which we'll see now will be similar to voting rules. We talk of dictators, we'll talk of majority and all such things going on there. And we want to distinguish. Well, so the goal is now for us, we are now going to reduce our work, is to design this sort of a test that distinguishes it. And reason it will come and be clear why. If you the past lecture will tell you why we want to design dictators. But for now, let's just take it that we want, this is what we want to do, we want to design a dictator. But the test will be a very simple test. It can be, it has to query two things and check if they are, and check some property of them. In fact, not one only, only property it can check is not all equal. Because that's the max cut. The max cut edge, what is the edge doing? Are these two guys on different sides of the cut or not? So that's the only test you can cut. So let's design the most obvious of the test, which I'm going to call the first attempt, not all equal test. First attempt. So once again, the input is this function, which you don't get to read in its entirety. You just get oracle. You can query it at any location. So pick x uniformly from 0, 1 to the k. Pick I uniformly from k. Query f of x and f of x plus ei. Actually, no, sorry. So I wanted to, I want to distinguish, dictators should pass the test, non-dictators should sort of distinguish. That's why I put the word distinguish in quote. I don't know how much I'm going to do it. So what is it? The only test I'm allowed is a not all equal test. I can query 2 points, check they are not all equal. I want to query a test that dictators pass. So if you query x and minus x, when I mean minus x, I mean I'm flipping every variable bit. So ones are flipped to 0, zeros are flipped to ones. So query f of f at x and what I'm going to call x bar. So let's make things easy. I'm going to use minus x a lot of time. So let's actually change my input to plus minus 1 to the k to plus minus 1. So it will be easier for me instead of writing flipping. So I'm going to pick a point this way. And so accept if f of x not equal to f of minus x. So that's the first test. So certainly dictators pass with probability 1. But it's not just dictators. What are all the tests that are going to pass this?
All the Fourier coefficients are out in
Every odd function passes this with probability 1. So that's not just one, but the whole bunch, any odd function, that's the definition of odd function, f of x and f of minus a, the sign flips when you go from any odd function. Yeah, that's just allowing too many functions. So what we want to do is actually something little more, so which instead of testing these two antipodal points itself, it checks points, it tests a whole bunch of points, not just two things which are far apart. It tests things which are of various distances. Here the test is only querying x and its antipodal point. So that's the only test. The only edges going across are these sort of every x is actually there's only a degree 1. The edges being put here is a perfect matching among the vertices. It's very few edges are being put. What KKM suggested was let's put far more edges. Let's put far more edges. Notice we don't know which dictator it is. We want to accept all dictators. If we knew which dictator it was, we can just flip the I bit and check it. We don't know which dictator it is. We just want to accept the dictator and reject dictators. So what they suggested, the KKMO suggested the following. So this test accepts all odd functions and is very sparse. Very sparse is actually a good feature, but because it is so sparse, too many things are passing the test. So we'd like to add more edges in it. So KKMO suggested the following not all equal test. What is the not all equal KKMO test? And it's going to get parameterized by an epsilon and 0, 1. We not call it epsilon, let me call it rho. Okay. The test is once again the test has access to F is the oracle has access to. So you pick X at random as before, from plus minus 1 to the K. Then this is sort of motivated from VLR. We're going to pick a noise function. So what am I going to do? I'm going to pick mu from plus minus 1 to the K as follows. Mu I is going to be 1 with probability 1 plus rho by 2 and minus 1 with probability 1 minus rho by 2. So mu is an independent, all the K coordinates are picked independently, and basically I'm going to toss this bias point with rho probability and decide this. And then let's set y to x times mu. By this I mean this is element wise Harman product. For accept if f of x not equal to that's simply test. These are just been discussed. Why? Let's for the next 5 minutes or so. Let's first find out how much do let's completeness. How much does a dictator? So if F is a dictator, what is the probability that they're not all equal rho test? Such F.
1 plus rho. 1 plus rho.
1 minus.
1 minus rho.
Then we change it.
Hmm?
You want to make a
It will
pop.
include the-
Probably have to move this.
Yeah, so
Bias equals movement.
so that means stated in my notes actually states with the other with rho negative. I think that's ugly, so let's do this. Should I even
My notes in this or this makes sense. You should like the thing is some kind of supposed to be markup. It's like it's a lazy markup chain or a property mark just remain put. And then otherwise you decide to flip or not with some random property. Then you get something else. Because then the probability of getting stuck
Yeah,
higher.
I see, no, that is fine, the question is whether they want row to be minus one to 0 or 0 to 1 is. Yeah, it's fine this way, let's leave it this way, we'll get to. This one. Okay, so that's. So,
Yeah, I would imagine it is down negative.
huh?
Yeah, okay.
You would want row to be negative, no?
Not with your impression. Because I would think that you want the mark.
No, we are going, but in this definition, rho is positive. In this definition,
The acceptance probability is less than 1.
so, I put it again, no? So I will keep what I had previously. Let's keep what I had. So I wanted to accept with probability this one. And rho is a noise parameter, or actually it's called the noise stability parameter. Not the noise, just the noise. And rho will be a number between -1 and 0 for us, right? No?
You also want.
This one, which is noted as a number greater than half, since rho is in -1 to 0. That's the completeness. Let's look at the soundness. Okay. Let's find that f plus minus 1 to the k, to plus minus 1, be arbitrary. So let's just write down in Fourier language what is the test acceptance probability. So this is exactly the probability over random choice of x and mu, probability of f of x not equal to f of x mu. So I want to sort of appeal to Fourier. So what we'll do is we sort of do this arithmetization step which you are familiar with. This is the same as, because these are Boolean valued functions, they take only plus minus 1. This is the same as writing this. Because if they are equal, this quantity is 1 and it contributes 0. If they are unequal, it contributes -1 and this contributes 1, and that's exactly what it is. So this is the same as above. The reason arithmetization is now I can appeal to Fourier. So this is exactly half minus half times expectation x mu f of x mu. So this is what we have here. So this is a quantity that we will see quite often. Okay, this is now I see why I had done this. So this quantity is something we will. This is an important quantity. This is called the noise stability of the function f. So let's define this quantity. And we define it more generally for any row between -1 and 1. This noise stability, called star row f, is basically expectation of f of x and f of mu times x, where x is selected at random from the hypercube. And so let me write it this way. So we need to look at it. F is selected this way. F y is, and y is selected to be a row correlated copy of x. That is, what I mean by this is at every location yi, expected value of yi is row times expected value of xi.
Correlation also.
Yeah, correlation. So yi is the thing. So with probability half, it is completely random bit. With probability rho, it is with the remaining probability it takes x. So that's exactly x. why is the distribution of x mu? You can look at it. If the x mu random variable that I have picked up will exactly have this distribution. This is just shorthand notation for producing, and this is x mu you have got this. This is you take f, so noise stabilities, you take f, you sort of produce a correlated thing, and you're asking does the function remain the same or different? Is the function different? This is called the noise stability of. Stability. So I want to ask how do dictators behave for this? How do non-dictators behave? And it should not be hard that if I open out, if I do Fourier for this will just turn out to be yes, so this is just this fact. This is just write down what is this? This is expectation of. I'm writing f in the Fourier, so it's f of s, f hat of s, chi s of x, summation over t, f hat of t, chi t of mu times x. So this is summation s t, f hat of s, f hat of t, expected value x and mu are independent. The random variables behave chi s of x, chi s of chi t of x. Chi t of the character chi t is multiplicative, so it's chi t mu into chi t times expected value over mu of chi t mu. This will force the only way this will happen is f equal to t, otherwise this is over 0 because these are orthogonal set. Therefore, f has to be equal to t. Expectation mu of chi t of mu, you can check it for the random variable, it's actually rho to the power mod n. So this boils down to summation over s square s rho to the s. Now, and what are we saying? Noise stability of tab row f of dictators is exactly good. And what if f was a linear function? Dictator is also a linear function. Dictator is a linear function which has support 1 xi. Suppose the linear function had support, it was x1 plus x5, x5 plus x10. It was a linear function, so f was product of xi, I in s. And what would that would mean just that particular Fourier coefficient is the dominant Fourier coefficient, is the only Fourier coefficient. Tab of such a function would be tab of linear functions with support. Yes, is exactly rho to the power of x. So at the very least, or as a function among the linear functions at least, dictator has certain. Of course, the constant function is extremely stable because it's not going to change. But the linear function as it gets more and more support, the stability is problem. So this one, at least this function, distinguishes even within this order, this one, the other linear functions, it's sort of tapering it out. Their probabilities which they are being accepted is lower and lower. So let's make several observations over here. Dictators. Then what I'm going to do is These are, I'm going to talk about various functions and their stability. So the first one is dictators. Row. Two linear functions with support S. Row to the modus. Of course, the constant function, what's its stability? So it's extremely stable. And yeah, it's a stable. Okay, so let's go now. What about the majority function? You're taking a random k-bit string. I'm going to flip. You're roughly flipping how fraction of the bits.
Little bit.
Yeah, you're flipping 1 minus rho by 2 fraction of the bits, and you're asking, are you going to go on the, so the majority is this cut on this one. Question is, doing this, do you go on the other side of the cut? By doing this sort of flip, do you go on the other side? And if your point was already very far from majority cut, this will not flip. The only things which are close to the cut might have a chance, because that thing could take you further inside also. The question is, are you going to cross the cut? And that's basically the thing we are asking. We're going to ask for the majority function. You're going to, as everything in the top is labeled +1, everything in the bottom is labeled -1. I have to pick an x and then move to that's x, and I move to x mu or the other way around for this stability. If I stay in the same thing, it's stable. Basically, stability and all other things are considered motive equals in that. If you have to pick a random motor, this thing is corrupted. One second, how best do I say this? No, there's an election rule happening. Certain number of voters, things get one. Just the nature of the, so F is some electing rule. It could be majority, it could be dictator or something. Pick up a bunch of candidates, they give their votes, we have function. Now, some person's votes gets merged or something. There's a fraction independently, it happens. Is the election rule stable to such sort of changes? That's what we are asking. And this is where exactly you can do this, and this happens to be the function that we care about. It's cos inverse of rho by rho. As n tends to infinity. As k tends to infinity. So, in some sense, what's going to, which you might be in a better question to describe. So, what's going to happen is we are going to take this random variable x1 to xn, flip it and move to the. See, you have summation xi. Summation xi is one sign, and then you're flipping each random bit by a particular thing, and you're asking, does this flip now change summation xi from a positive value to a negative value? And this is very much related to summation xi looks like a in the limit as k tends to infinity, it looks like a Gaussian random variable. And then there's a correlated Gaussian random variable, summation xi mu I is also a correlated random. These two basically behave like two correlated Gaussian random variables, which a correlation is being rho, in fact. And you're asking, if I pick two correlated Gaussian random variables, what's the probability that they are of two different signs? This is exactly what happens, and this happens to be cos inverse rho by mu. Right? And so majority, this one happens to be this quantity. Let us. And
Sorry, and the original paper that rejected precisely this.
no, this was a known fact. This is a known. This can be proved. This is whatever I said now can be made into different proof. That is basically this is kind you have summation xi and summation xi mu I. You're asking what is the
Question is the best. Right. Nothing else.
Yeah, so how big is that number?
Huh?
I don't what.
Yeah, the question is, yeah, it depends on, you have to go into causes. So, no, this is Shepard's formula, but what is okay?
Cos inverse row.
He wants to know
Compared to row.
Oh, no,
Rows square.
oh, that, cos in,
so you want the Taylor series of cos basically, no?
cos inverse, it's also, yeah,
Is this why 7 that is lower?
Yeah, this is why
that's also related,
uh,
I mean, in fact, that is also the same calculation, right? You basically are looking at two random vectors on the, on circle. And you're looking at, so, or rather, you have two vectors in the circle, and you have the inner product, and you want to look at what is the probability that you land up in between. That's where the computer.
And you get only an angle.
Yeah, and this, but it's
so what I'm just pulling this off. Wolfram, I'm hoping is correct. So cos inverse
like 5/2, right? So,
cos inverse of x is it's
And
centered at pi, cos inverse of 0 is pi by 2. So it has to start off with pi by 2.
the possible is 0.
I'm doing it around 0.
okay.
Pi by 2 minus x cube
That's,
by 6 and so on.
that's,
That's like half minus the.
yeah. So this is among all functions which are bigger balanced. This will be the highest possible. In
That rules out the common function.
Yeah, I think that's the answer.
So what the question is, so majority has a fairly large this one stability. Dictator has rho. They ask, so majority certainly comes as an issue for us. The majority is also having extremely good stability. In fact, that's the reason why majority is a voting rule. It's possibly one of the most stable rules. Question is, are there? They are, so the question they ask is, unless discussed, are there other functions like majority which also have a so stable and stuff? And at this point, they came a conjecture the following, which then was shortly proved by this one, that if any function is a little more stable than majority, it has to look like a dictator in the sense that the function should have an influential variable. Majority is something which has no influence. All the participants play equally. It says if the function has influence slightly better than majority, stability better than majority, slightly better than this one, then it must be that that function has an influential variable.
But sorry, the dictator doesn't have. Does the dictator have?
Yeah, it has a one independent.
The dictator is implicit.
That variable has.
No, what is the stability of the
No. The stability of the dictator is low, I agree. But the point is, the stability of majority is even low, even better than dictator. I want to kill out majority like function. So I want to say, if anything does better than, so we will have a proof which eventually deals with majority. And we'll say if anything does better than majority, it has to be because it's dictator like. It has an influential variable.
So in some sense, the worst case in the proof is going to be these majority like functions.
Majority like function.
And then you're or are you basically saying there are two extreme cases? One is majority, one is dictator, and everything is one of these two. Is that the kind of thing?
Yeah. So the proof will be able to handle dictators, majority, and then we'll say that if anything, we want to say basically these are the only cases. And this theorem is what is going to say. This is a theorem of, this was originally a conjecture, but now this one. So first I stated informally, and then say if f going from plus minus 1k to plus minus 1 has stability greater than or equal to cos inverse rho by pi plus epsilon, then
Oh, I see. So yeah. So what I was you can't just say, so the thing I was saying that you have that the majority should be stable somewhat balanced, that cannot be true just because you will take majority on something like 0.9 times and
Yeah.
it would be similar.
yeah, it exists an influential variable. That's what we'll show. What now I had to define what does it mean to have an influential variable. We'll do all of this.
So, sir, what is the influence?
Yeah, that's what going to do next. So this is the theorem code. So we have to define the influence of a variable. So I'm going to define in phi of f. It is going to be the natural definition. You pick a random point, you flip the ith variable and ask, does the function change value? The function changes value, that means I has at a location you're saying the ith coordinate has an influence. If at that location, if you flip it, the function value changes. But you're going to do this expectation over everything. So it's exactly the probability. The probability you pick a random x, f of x not equal to f of x plus even. I'm going to keep flipping between the 0, 1 notation and the plus minus. So technically this should be x times e of I. E of I in this world does that. So you can once again do this. You can write it as expectation x of 1 minus f of x ei by 2. Open out the Fourier. The only thing you'll get are summation f hat square s, where s contains time. Only those things will remain in the Fourier. So that's, and let's look at what are the examples. So let's look at influence of dictator. So say f is xi, then the influence I of f is 1. It's an extremely influential variable. If f were the parity function by s, influence I of f is it's 1 again.
One is revising this or
Yeah, so 1, so it's 1 if I is in S and 0 otherwise. And this is also the same thing here. So that was the xj. So this is it. I equals j, it's going to be 0 otherwise. F is majority. So it's basically you have to, x should be one of the middle, x should exactly, for the n is lesser, n, k has to be odd, and x has to be the middle layer of this one, it has to flip. So that's approximately like theta 1 over root k. Parity of course is 1, parity is is when s is the So this will be statement we want. We'll actually work with not just this notion of influence. We'll actually work with a slightly modified notion of influence. What's called the low order influence. This is influence I less than or equal to d of s and less than or equal to f. This is just f hat square s for s such that f has to contain I and mod s less than or equal to d. We just don't look at all the okay. And what the majority stateless theorem is going to say is the statement of something of the following. It states that if a function has influence slightly, if it has stability slightly better than majority, then there must exist a variable for which its lower order influence is large. So let me state this one. This is the what is called the majority stablest. Here. So any row in -1 to 0 and epsilon in 0, 1. There exists tau in 0, 1 and t greater than or equal to 1 such that if have row of f is greater than or equal to cos inverse rho by pi plus epsilon, then there exists I into k such that the lower order influence is greater than or equal to k. In that sense, this is the soundness analysis for the test. We are saying that if the test passes with some probability, it looks dictatorish. That is, majority will pass the test. If the test passes any better than majority, then there exists an influential variable. That's so by the way, this theorem was at the time of KKMO, this was a conjecture. They conjectured it and it was immediately after proved by Moser or Donovan and Discreps. Now let's return to our. We are now going to now plug this back. So right now, why did we do all of this? Started all from this picture. We were going to do this reduction from unique label cover to max cut. And we had wanted to do the gadget reduction, we're going to blow up each vertex in the unique label cover to a cloud. And then we had to put edges across. So there are going to be two types of edges, edges over here, edges across the clouds. We forgot about the edges across the clouds, and just edges over here. We wanted to unlike some features, we wanted to say that if function does not, if it passes with reasonable probability, it should look dictator, right? And all of this was to go towards that. Now you could now ask, okay, now I have to actually build this violet colored graph, I have to do this. There's a slight issue with this if I'm dealing with max cut. If I build a graph like this and with cross edges, this has a max cut, a very obvious max cut sitting there. Basically, everything to the left is on one side, everything on the right is one side. And this is going to cause a problem there. Such a cut is going to cause an issue. We don't want to have such a cut. So what we will do is we will not put vertices on one side at all. We'll take any guy here, we'll go to this one, and instead of putting edges between, we'll have only vertices in one side of the cloud. Instead of putting edges for every edge here, we'll take an edge this way, a blue edge this way, a blue edge this way, and then put an edge between. Anyhow, it's a permutation. Therefore, if between these two there was a permutation among the constraints, and these two there was a permutation among the constraints, between these two there's a permutation among the. So we will actually work as if the vertex, the unique label cover is actually on just one side and do the whole.
But does it preserve the value?
It doesn't preserve. We will work. The assumption will be on the bipartite graph. But what we will do is we will put the thing on the. We will only draw this. Yeah, I'm not changing the. Yeah, so now let's go on to the reduction. So the reduction from ULC to max cut. So the input is an instance P of the form G U V E sigma and psi, and psi are all uniques and for permutations. Special constraints and so I'm now going to specify. I have to specify what are the edges. This will be a weighted graph. Weighted graph. So the edges, the vertices of this graph are going to be take V. So the output is the graph G, which is E comma E with and a weight function. E is just going to be B cross 2 power sigma. That's everything I've blown it out of your flow. That's the set of vertices. And so suppose if I give you this, a cut is just specified by the cut is just specified by this. So, so I'd actually specify the edges and the distribution. What I will specify is the queries which I'm going to make don't to specify the edges. I'm going to say I'm going to pick up these two. So FB is a cut. Okay, think for now, just don't think of it as anything right now. Just floating out there. All I have to specify the vertices. I have to specify the edges. Edges are all going to be all pairs which my test is now going to query. And what is it going to query? The edges are going to be picked in the following fashion. First, we pick U at random from the left hand side. Actually, we should pick the probability proportional to degree of U. And if you assume the graph was biregular, then it's just a uniform distribution. Otherwise, I'm picking a vertex with probability proportional to the number of edges going out of it. To pick V prime at random among the neighbors of pick two guys at random and phi u v prime be the corresponding permutation constraints. So the edges, basically, if you pictorially, if we have this, with the U here, with the V prime. This in our picture has gone to a cloud. This has gone to a cloud. So the distribution is so we have clouds for every one of the right vertices. So if I'm going to put edges between them, there are going to be no edges within a cloud. All edges are going to go across clouds. There might be edges according to V and V prime happen to pick the same. This one. So the way the edges are going to be decided this way. First we pick a random U according to the right probability distribution. Pick two neighbors V and V prime. Now go into their respective clouds. And then once you go into their clouds, pick X at random from plus minus 1 sigma. So I'm going to pick one guy at random from here. I'm going to pick X mu over here. Then 4 is. Let me state this just. Okay, and pick y to be row correlated with x. Let's pick mu and then do this. Okay, so this will be y. Now, the previous test was the test if actually these were the same constraint, we would have checked them exactly. So if the constraint between so the way it's going is v, there's a permutation constraint going this way, and there's a permutation constraint going this way. Let's for simplicity assume that when you compose these two permutation constraints on sigma, so this is just a thought experiment. This is v, this is sigma, this is sigma, this is sigma, but sigma when viewed from v's point of view, u's point of view, v prime's point of view. So there's a matching here, then there's another matching here. That's how you compose them. Let's look at this product compose matching. If it were the identity, then the test we would have done is exactly the test which we had done before. I've checked that f of x is query this guy at x, query this guy at x view, check that they are not equal. Because they will have to give the same label. They both have to have the same label. So what? But because it's of this phi, I'm going to have to change certain things. So what we instead test is the following object. Accept if fb of x composed with phi ub is not equal to fb prime of y composed with phi ub. I think I got this right. And what does x composed with phi ub? No, I mean it just means I'm going to.
It doesn't be
Huh?
doesn't x compose with phi u comma p using the alphabet of p.
So when I haven't even described what that notation is. When I mean x composed with phi ub, it's just telling I'm relabeling the coordinates to relabeling the coordinates so that this coordinates they were labeled 1 to sigma this way, but label it as if they are from here. And here also relabel it as if they are from here, so that now you are talking about the same thing and now check it. That's what I mean. I hope that's what I mean. I hope that notation means that, but that's what I mean. There's a labeling of the coordinates over here. Because of this matching, you can think of it as a labeling over the coordinates here. You just relabel the coordinates according to this phi ub. Similarly, relabel it here. Now they decide on the same thing and now run the not running test. Fair enough? So these are the edges. The edges are between that vertex, and what is the probability you put on the edge? Exactly the weight that you have picked it up. And f is you are given some cut, which is defined by f, with a bunch of fb's, and you're checking how good is this cut. Is the graph clear? And the definition of graph, I'm mixing the cut and the graph. I should not talk about the cut at all when I talk about the graph, but it's easier for me to write it in this language because what I mean is there's an edge between this vertex and this vertex, the probability proportional to those, that's the edge. So when you're doing the cut, that will be whether this will be the probability that if you have that cut, yes, this will be checking whether that cut edge exists in the graph or not. Okay. So let's do the easy part of the thing first. Let's look at completeness. What I want to now say is if the graph, if the GLC, the completeness is this kind, if P is a ULC instance with val of P being greater than 1 minus delta, then the cut value, that is probability that is the max cut, then what I want to say, then there exists an F, there is one cut on there exists an FB plus minus 1 sigma to plus minus 1. So there exists one. If this was actually this one, then there exists a cut, which is a cut is basically a set of all functions for every vertex and then such that this cut will pass this test with some probability. Probability that max cut. So this I'm going to call the KKM of max cut. Test. That is called the KKM test. Next. How much is this going to be? So we have to prove this. I'll have to do this, but let's see what it's going to be. So what? So firstly, I will tell you what FB should be. Huh? So just choose FB to be the dictator. So choose FB for each V. So since val phi is greater than 1 minus delta, so there exists labelings A from U to sigma, B from B to sigma, that probability when you pick an UV, psi of UV of AU equals BV is greater than 1 minus delta. So that's, you have this labeling B. So now let's define for each V in capital V, let's define FB to be the function which basically is the dictator function, and the dictator is given by the coordinate B of V. So let's define FB to be the dictator given by B of V. B of V is specifying a coordinate, make it the dictator corresponding to that coordinate. Now let's stare at this. Suppose this edge was satisfied and this edge was satisfied in the coloring this one. What would by the AB this one? BV will now when you coordinate it, this will become x of BV will become x of AU. This will also become x of AU. So the probability, what is happening here? The probability not all equal is actually it's exactly 1 minus rho by 2. This is what I want to say. So this is probability that 1. The two edges should both be violating edges. They will both be satisfied edges. That happens with probability 1 minus 2 delta.
What did you take the value?
Huh?
What did you take rho to?
I haven't yet said rho to be anything. Rho is free right now. So this is parameterized by a rho also. KKMO, there's a rho floating around here. So I want to claim this is delta into 1 minus rho by 2. So this is greater than or equal to sum 1 minus rho by 2 minus sum epsilon. That's what I want to create.
So in this whole crucial point of the KKM test had been just compared inequality, which is the same constant as math.
Yeah, that's the whole. So you want to design a test. Yeah, this is something which we have seen before. So once if you want to do something for it, so this sort of.
You can do pre-processing before, but in the end the test will only be one.
Yeah, so this picture which we had here. So from label cover, if you want to do any reduction to a particular problem, say max length or max sat or something, we'll eventually blow it up into clouds like this, possibly one side, two sides, I don't care. And then you have to query if you had the parity of the constraint is 3, you have to just query 3 guys, and the test should exactly be whatever. If it was a max sat, you should be querying only the OR of what you're reading there. If it's a max lin, the parity of the 3 things, max cut. So this is why what the function is really important over here.
So this is where we use the fact that it's a one-to-one game.
Where
That you can lift alphabets in B1 to that of B2 higher.
this actually didn't require one-to-one, it only required if it was projection from these two to that. The test would
You would have required that every level in B corresponds to a unique level in Q. And that unique level in Q corresponds to a unique variable.
we are only coming from these two Q. So strictly speaking, the way I have defined the test, I only need projections this way. It's the analysis where somehow I will need the other guy also. Projections have to come from V to U. If I had that, I could define the whole operation. Okay.
So far also the analysis also is not been rated, the projection would have worked even now.
The projection will work right now. It's the later part of it. So what we are going to prove is the following.
This is one of the, this is the soundness or what, no, this is the.
Not at this point. This statement of soundness will not. So no, we are already I think the statement the way I have it will require. I'm going to have the soundness claim. So let F be a cut that satisfies a significant probability. So suppose this family of FB, V and B is a cut. Is a cut such that probability that NO the row F accepts is greater than cos inverse rho by pi plus epsilon. It passes better than what the majority cut. So then what we will show, then there exists a labeling A and B that satisfies more than delta fraction of ULC constraints. Strictly speaking, the way this will go is for all rho epsilon, there exists a delta such that this happens. And this will violate the soundness of. So telling you the test passes with both the probability cos inverse rho by pi. This one, if it passes, is probably better than this. And I'm stating that actually you can satisfy more than delta fraction of constraints. So what do you get for this? You get that it's hard to distinguish between 1 minus rho by 2 and cos inverse rho by pi. That's the gap. Now from this, find the best rho for this. This is exactly what Gomez-Williams also did, and that happens to be 0.878. So if the soundness claim which we I didn't get is true, then what then the conclude corollary of this is it is UG hard. Assuming the hardness of UG assumption, basically it's a reduction from ULC to this UG that is what I'm stating is for all rho and epsilon, it is UG hard to distinguish between max cut instances with cut size at least 1 minus rho by 2 plus epsilon and cut size at most cos inverse rho by pi plus epsilon. Therefore, this ratio, you cannot beat this ratio.
For any
For any row, you pick the row, your choice.
and that is the one
That exactly, this is the same maximization problem that happens in.
and that is because of the same reason. Because
It's the same,
the
isn't it?
majority thing is exactly that same problem that you're
Yeah.
looking at two vectors and you're in the sector.
And Shepherd formula also you are analyzing the probability of time. You can just say
What is Shepherd formula?
that if you have two row correlated variables, then what is the probability one of them is gap of zero and the other is there.
No, so in normal for the Gaussian derivatives, it's a I don't know if that's called Shepherd formula. That's very easy, right? Because the point is that the row coefficient just means that one you can
One is
think
inner
of.
product of U and that is inner product of V and their angle is.
Yes, I mean, we can think of one as x and the other one as rho x plus the square root of 1 minus rho square y, where x and y are independent. And so it just becomes, because now, so now if you draw the picture into, it's like a,
It's the same analysis that
it's like, yeah, so you will draw this rho x plus 1 minus rho square y line.
but in the inequality of performance we also have the same probability right, that the hyperbolized people.
Yes, well, in the rounding and the integrality both.
Yes.
Yeah, yeah.
So if you choose the row to be something like very close to -1, so it's like closer to be -1 plus epsilon. Then this guy becomes something like -1 plus mu. This guy becomes something like 1 minus mu. So you are talking of a graph which has cut size very close to everything. If the cut is 1, then it's easy to distinguish because that's a bipartite graph. So I'm talking about graph whose cut is 1 minus mu. Almost everything but mu fraction of the edges. They exist at a cut. That case for when rho is like -1 plus mu, you can do the expansion around this. This happens to be 1 minus square root, order square root mu. So you will get for graphs of cut size, graphs whose cuts have cut size is 1 minus mu. It's going to be hugely hard to find out the cut size, the distribution graph whose cut size is 1 minus square root mu. And SDP exactly comes up to this point. Like if you give a graph which cut size is 1 minus mu, SDP will find out cut of size 1 minus square root mu. SDP meaning Gomez-Williamson algorithm does it. Because Gomez-Williamson algorithm exactly does this. If the cut size is this, it will output a cut size of this. So that is the what I call the corollary here is the AKM here. Okay.
Yeah. The other is that the point is that the variables that appear in the SDP are the inner product vectors, which is like rho here. And then in the end, what the calculation you do is find the angle between them, which is cos inverse.
Yeah.
And that's the so there the objective function of 1 minus rho there.
The objective is the dot product. Yeah. If you recall that, that's exactly what
Yeah.
happening is.
1 minus rho versus cos inverse rho, which comes yeah.
So there is 1 minus rho, and here it's cos inverse of rho by I think it's cos inverse of rho by pi by 2, no?
Yeah, well here it will be pi, or maybe there is some, but it's the same thing.
It's exactly the same thing.
The width of two vectors is a certain inner product, which is rho. That is what will show up in the objective of the conventional STP. But when you do the analysis, that will you will actually get that with the probability that your random vector actually goes between these two vectors, which is cos inverse rho by So whatever the angle between them, which is cos inverse rho by pi by yeah, because two times cos inverse rho by cos inverse rho by pi. So that's contributes 1 minus rho there. So yeah, so the gap graph doesn't explicitly come up here, but it's sort of there implicitly. So there is this Peigen is after this or before.
Peigen is right after Bunsen. Peigen is gone. It's 96. Immediately after. Peigen gave an integrality gap instance for the max cut problem.
Yeah, that is also a pretty amazing.
Yeah. So this is exactly I just mathematized the one. So we are starting the assumption that this is greater than cos inverse So this is greater than cos inverse rho by pi plus epsilon. So by averaging argument, for at least epsilon by 2 fraction of vertices in U. In capital U, we have expectation of V and V prime. That is, I fix a particular U and looking at only its neighborhood set now. X mu 1 minus this one, whatever, right? By 2 is greater than equal to cos inverse rho by pi plus epsilon by 2. Okay. Now I can sort of push. So let's push the expected V and V prime are picked independently. So I can put the expectation inside. So this is the same as stating 1 minus. So let's keep this expectation X and mu, I can't push it outside. So this is 1 minus expectation on V. By the way, this is not a random V, it's V only coming from the neighbors of U. That's the distribution here.
So is it at least epsilon or at least 1 minus?
Huh?
So
I have assumed globally it is epsilon. This is this quantity.
it's epsilon and so
Therefore, for at least epsilon by 2, it has to be this quantity.
It should be a epsilon of 1 minus.
So the thing is that whatever is inside can be at most 1. So if on the epsilon by 2 remaining fraction it's 1.
It should be half in
Then on
the.
Oh no, sorry.
Now what I do for less than, if it's for less than epsilon by 2, if this is less than epsilon by 2 fraction have this much.
Yeah, then the remaining can contribute 1.
So that will contribute epsilon by 2. All of this could have contributed only cos inverse rho by pi plus epsilon by 2. Therefore, totally they could have contributed only cos inverse rho by pi
Yes,
plus
that
epsilon.
should be at least 1 minus epsilon.
No.
So the point is suppose that there is a more than epsilon by 2 fraction. So more than epsilon by 2 fraction where it is less.
Yeah.
And the remaining 1 minus epsilon can contribute 1 minus epsilon. Then.
And you can contribute 1.
Yeah, so but the total contribution is 1 minus epsilon by 2.
1 second. No. Suppose the quantity that contributes more than this is less than epsilon by 2. Suppose the quantity that contributes more than this is less than epsilon by 2. This epsilon by 2 can contribute all the way up to 1.
Yes.
So,
Okay.
so this contributes epsilon by 2. The remaining contributes only so much. Yeah. Notice why am I doing all of this exercise right now? Notice this is not exactly the form I can apply the theorem. In the theorem, I need the same function, stability. This is almost like the stability function, except it's two different functions being put over here. This is FD, x naught phi u prime, that's FB prime, except this one. Stability theorem, and we do this. But once we bring this expectation inside, now let's define GU of x for all the good u's to be exactly this quantity which we have. Its expectation, you pick a random neighbor from U, FV, XO by UV. Do this. Then what we have is for every good vertex, for every good V, we have expectation value of x mu 1 minus gu of x, gu of x mu,
Every good U, every good,
huh?
every good U.
Every good u, yeah. I thought we should take a break. No, the battery is constantly running out.
Oh,
So that's why.
no, but it says 25%.
No, that's the.
Pencil.
Oh, pencil, but yeah.
That's why I have to put this and I'm stuck in hands go back. So this is what we have. But now what do we have? This is exactly the form which we had then. So if this is larger than this will say this has to have an influential variable. So each GU has to have an GU is not the cut between, GU is sort of this average function which never existed, it's the average of one, but GU has to have an influential variable. This is what we have got at the end of this. Okay. So what do we have? So by the majority is stateless theorem. For each good V, good U, there exists
Recording in progress.
an influential variable.
Is it low degree?
Yeah. So I will write down what that means. So that is, so let's call it the variable JU in sigma. Such that influence of JU less than or equal to D of the function GU is at least 1. Okay. So now, okay.
Yes, I was trying to see if I can also use this tablet to value answer.
With fact that I have this one, so pencil, check it. Thank you, of these bottles. So just tell me, okay, you already. Let's. Is it the? Yeah.
But that's probably better than trying to change the tablet.
Okay, so this tells you there's an actual labeling for the left vertices. What's the labeling? Just give it the influential variable. So this define, I had to notice I had to define the labeling for both the left vertices and the right vertices. So define the left labeling. As A of U is exactly JU. Now we have to define what's the right labeling. So let's look at that a little carefully. So what is GU of X? GU of X was expected value over the neighbors of U of FV of XO by UB. Let's write this in the Fourier notation. This is F hat V of S chi S of XO by UB. I've done nothing so far. This is expected value of V, summation F hat V of S. Chi S of XO pi UB is just applying the permutation on the set S. So it's chi of pi UB on the set S of the non-variable X. That's just relabeling the columns. Here. In the next step, I'm going to sort of. So this is almost like the Fourier expansion for GU. It's not the Fourier expansion for GU because it's sort of averaging of several guide segments. So I would like to pull out, what I would want to do is write this fact. I would like to write this as summation over T, some expectation of some quantity, phi T of X. So because now this is the permutation going the other way also, this is exactly pi inverse UV P of X. So this will be f hat V of pi inverse.
I got.
Is that okay? Here I am using the factors on the other way. So projection was used to define the unique one way was used in one way. Here I am using it goes the other way. So we have this. And what we do know is that guy has low order influence. Now we will use that from that to show that this guy also has sort of low order influence. So in particular, what we get that G hat U of T is the average of F hat V of these guys. So the Fourier coefficient of G for a particular T is actually the Fourier coefficient of related FVs in this. What do we know? We know tau is greater than or equal to influence of JU less than or equal to D of GU. This is by definition summation over all T. T contains JU. Size of T is less than or equal to D of G hat U of T squared. Let's just plug that formula in. Right. Yeah, so it's an expectation of x square, expectation of x the whole square. We use Cauchy-Schwarz to go expected x square. So we just go, so this is summation T containing JU mod T less than or equal to D expected V. This expected square. That's just Cauchy-Schwarz. But now what is this? Because it's a permutation, this isn't it exactly? So every set of size T is going to get to another. So this is exactly the
Low degree influence of the.
of not JU, but the image of JU.
Yes. Pi inverse.
So it's going to be, this I claim is exactly expected value over P of the influence less than or equal to D of pi inverse UV of JU of the function F. So what do we have? We know that we know that on average their influences is large. Therefore, a good fraction of these guys will also have an influential variable. For all of them, you define them to be this, and that is going to be the entire. So once again by an averaging argument. tau by 2 fraction of neighbors of U satisfy influence less than D pi inverse UV JU FB is greater than or equal to tau by 2. Now let's look at, so now that defines for, so you just go, you look at by the way, so this is cannot be so there is an influential variable, so you cannot, how do I pick it up? This is fine, that was fine. So so the question is how are we going to label these guys? Question is, one thing will be just go ahead and label B with pi inverse UV. This is not a label I can give to it because it depends which neighbor this B is coming from. You what the neighbor U prime will say you this guy, the neighbor U will say this guy. So there might be different choices I'll have to take. This I am not told you that pi inverse JB is a function just dependent on V. It's not dependent on U you are coming from. But what I do know is it is an influential variable. The number of such influential variables can't be too high. So let's for every set, let's define SB to be the set of the J in sigma such that influence less than or equal to D of J of FB is greater than tau by 2. The claim is this guy cannot, how many tau by 2s can be there?
Almost 2 by 2.
No, not this one, because if you sum these guys,
Will be almost radians.
If this was influence with no.
Yeah.
Then
D 2D by 2.
it will be, you can go, what's the sum can be at most.
Answer not is a at a square not is less than equal to 2D.
And what I want to claim the size of SV is at most
2D by 2.
2D, yeah, 2D by 12.
So if F is sigma,
Huh?
J is sigma.
J in sigma.
So which are the okay, yeah, D, yes, D, yeah.
So which are the guys? So all I want to do is that since
And that's why you need the low order instead.
That's why you need the-
Otherwise it become N over.
since summation
Or sigma.
influence, yeah, this is why influence I less than or equal to D size of F over all I is at most D times, it's at most D.
Yeah, because
Each guy can appear at most D times, therefore it will be just a total part square as you are using Parseval and each by appearance, so this is
every set can appear at most size times and the maximum size is D. And then Parseval says
Yeah.
the element.
So that's why I need to lower the influence. I get D, each one is at most over 2, therefore assign it as we see. So what we do is, I don't know which one, but there's only a short list to pick one of these at random and assign it. So PV, the labeling P from V to sigma is pick a random sigma in SV and label it.
So is it easy to see why all these losses don't matter? Like you have the epsilon by 2, then tau by
We will
tau.
just see it right now. We will. So what is the probability then eventually? So I have defined a randomized labeling A and B. What is the probability that
Oh, because that one is good. That one is really good.
psi B AU
Just existence.
equals BV? This is what we need to compute. Over the choice of U, V, and another random.
And this one satisfies tau by 2.
So firstly, epsilon by 2 of the guys. So firstly, U should have been picked up in a good fashion. That's epsilon by 2. Then among it, V should have been a good neighbor. That's a tau by 2 fraction. And among the good neighbors, I should have picked up the right choice. That happens with probability the tau by 2d. Therefore, this is the probability with which I will pass the test. That's the lower bound. Therefore, epsilon tau square by 80. I now just choose the ULC delta to be smaller than this.
Oh, because the
There I have control of how small I can make delta. So you choose
with the connected everything is part.
choose delta to be smaller than epsilon t square 80. So you're having a covering which
It was crucial that these bounds on tau and d are independent of sigma.
or independent of
Including delta smaller sigma. will be low.
Yeah. So all of those statements were the way I stated it was majority stateless. It's important. So for all there exists tau sigma, and then comes the function f. So to make it further, let's say for all k, so all k, all and
So
function.
these are dimension independent quantities that
Yeah.
are contact. They will apply
That's
for
right.
every on every
Yeah.
every
So it's a constant that the label was a constant, but these constants don't depend on that constant. That was important. Get it out. This there's a lot of calculation here. The calculations are extremely minimal in this group. Calculating bunch of averaging. The things are the main statements. That is, you coming up with UG, coming up with a statement of majority stabilist, and putting them together. Putting them together actually is really not much.
So what does the two to two theorem mean? Is like if you relax.
For max cut, I don't know what it means. For so what is 2 to 2? If you do this 2 to 2 for max cut, I don't know what it means. For vertex cover, it recovers sports, it gives you square root. So square root 2 now has for vertex cover, it's moved from 1.3 to 1.
18 years that
Yeah, it's moved to over 4. It has to move to 2 eventually. Yeah. So yeah, that's where we are. Okay, so this is what I promised to do in 30 minutes.
Read the
Should we want to do it or should we just break for take over? Huh? There's a class, there's a, but there are people over sitting in that class. Like anybody here sitting in that class? You're sitting in them. When is that class? 2 to 3:30.
Yeah, it's at 2.
you can try to bully them.
We discuss. I sent an email by lunch. Sometimes I would like to be done with UG and this one.
Are you meeting after that?
So we need it to be after lunch around 2-ish. I will check with Ram Prasad. You can attend either, no?
I mean, I have to leave at around 3-ish, but I have things to do.
Yeah.
Which I'm doing.
So given that, should we actually do this on Tuesday? Let's do it on Tuesday. But it's already affecting. I thought it was not this, but I think there's a lot of ideas. Yeah. I don't want all this.